Good afternoon. This file contains the pre-lecture notes for class on Tuesday, October 8th, as well as Thursday, October 10th. There is only one pre-lecture video for the entirety of the next week of class. The relevant reading for this pre-lecture comes from the end of the Carey chapter, sections 4.5 through 4.18. Recall that we already did the beginning of the Carey chapter in earlier weeks of the semester when we talked about the different types of functional groups, as well as learned how to name alcohols and alkyl halides. For this pre-lecture, we will be focusing on the reactivity of alkyl halides and alcohols with regard to substitution reactions. In the previous week, we've looked at elimination reactions and their reverse reactions, the addition reactions. This week introduces a new type of reaction, the substitution reaction, that can also occur at an alkyl halide or an alcohol functional group. This reaction is different than elimination reactions and addition reactions in the sense that it does not involve either the use or production of an alkene. For this week, we focus on two different types of substitution reactions: halogenation of alcohols and halogenation of alkanes. These reactions are called substitution reactions because we're substituting one functional group for another functional group. In the case of halogenation of alcohols, we're replacing an alcohol with a halogen, X. In the case of the halogenation of alkanes, we're replacing hydrogens with X to form alkyl halides. In both cases, we're creating new functional groups from existing ones. So first, let's just review briefly the dipole moments of alcohols and alkyl halides. Remember that both alkyl halides and alcohols are polar, right? They have polar molecular bonds in the direction of the heteroatom. So for the alcohol, the dipole points in the direction of the oxygen. For the alkyl halide, the dipole points in the direction of the chlorine. The result of this is that in both of these functional groups, we get a partial negative charge on the heteroatom and a partial positive charge on the alpha carbon that the heteroatom is attached to. Because of the partial positive charge on the carbon, that is alpha, in each of these structures, it can be attacked directly by a nucleophile. In the previous weeks, we've looked at things like beta elimination reactions, where hydrogens are removed from beta carbons in order to create pi bonds. In this case, we're going to look at nucleophiles attacking the alpha carbon directly instead of the beta hydrogens. On this slide, I've included some common examples of substitution of alcohols by hydrogen halide reactions. Notice what's common in each one of the reactions. Here up top, we can see that the blue OH group is being replaced by a red Cl group to convert tert-butyl alcohol into tert-butyl chloride. In the second scheme, we see that the blue OH group in cyclohexanol is being replaced by the red bromine in hydrogen bromide to produce cyclohexyl bromide. And down at the bottom, we can also see that the OH group is once again being replaced by a bromine, this time in heptanol, to form heptyl bromide and water. Before looking at the mechanism of substitution of alcohols, let's talk about two factors that affect the relative rate of the reaction. The first factor that affects the rate is the nature of the halo acid used as a reagent in the reaction. From decreasing reactivity to increasing reactivity, we move down the periodic table from fluorine to iodine, with hydrogen iodide being the most reactive of the halo acids in this substitution reaction. Second, the structure of the alcohol itself affects the rate of substitution, with more highly substituted alcohols reacting more quickly than less highly substituted alcohols. As you can see on this slide, tertiary alcohols react faster than secondary, which react faster than primary, which react faster than methanol. This relative rate of reactivity should tell you something about the mechanism by which this substitution reaction occurs. Think back to earlier mechanisms that you've learned about in this semester in which tertiary functional groups react faster than secondary functional groups. Recall, all of those mechanisms involved carbocations. That's a good clue that substitution mechanisms also will involve carbocations. Let's take a look at the mechanism for the halogenation of alcohols to see that carbocations are involved with the substitution of a halogen atom for an OH group in an alcohol. Let's consider this reaction on the slide, the reaction between tert-butyl alcohol and hydrogen chloride to form tert-butyl chloride and water. The accepted mechanism for this reaction involves 3 steps, and we call it the SN1 mechanism. SN1 stands for substitution nucleophilic unimolecular in the mechanism. If it's a unimolecular mechanism, remember it only depends on the concentration of one of the substances involved in the reaction. As before, that substance will be the alcohol in the rate determining step. On this slide, you can see 3 steps listed out together for the SN1 mechanism of the halogenation of alcohols. Again, this is a stepwise unimolecular process, as indicated by the 1 in the name SN1. It has multiple transition states that include intermediates, and the 3 steps are as follows. Step 0, the alcohol is protonated by hydronium to produce an alkoxonium ion. You've seen this before. The oxonium ion then dissociates to form a carbocation. You've also seen this before in your elimination and your addition reactions. Okay. What's different in substitution reactions is that the final step does not involve an elimination or an addition, but instead involves the attack of a nucleophile, in this case a halide anion, directly on the carbocation to form the alkyl halide. We'll take a look at each one of the steps in this mechanism with regard to drawing our curved arrows, and we'll follow up by looking very carefully at the thermodynamic plot of the relative energy of each intermediate and transition state in this mechanism to understand the energy involved in the transformation. Step 0 of this mechanism should look very familiar to you from the elimination and addition reactions in previous weeks. In this step, the alcohol molecule picks up a proton from a nearby hydronium molecule to become an oxonium ion. Right? This step in the mechanism is very fast and is bimolecular because it involves the transfer of a proton between 2 oxygen atoms. The oxonium ion down here now becomes quite a good leaving group and can dissociate to become the carbocation, which is the next step in the next step in the mechanism involves the dissociation of the oxonium ion to form the carbocation, as we've seen before. In this case, the leaving group leaves and we're left behind with the tert-butyl cation and an H2O molecule. Because this step of the mechanism involves bond breaking without any bond making to compensate, it is a very slow step and is very high in activation energy because we're creating an intermediate carbocation that is very unstable. The final step of the mechanism is the step that differs from the previous mechanisms you've seen earlier in the semester. In this step, the chloride anion directly attacks the carbocation to produce the tert-butyl chloride product that we predicted in the beginning of the lecture. Let's take a look at the reaction coordinate diagram for the potential energy of each step in this mechanism. You've seen these diagrams before in your textbook, but we'll step out each step of the mechanism here together to make sure that we understand how to read these diagrams. The x-axis of every reaction coordinate diagram is the reaction coordinate, which you can think of as the progress of the reaction over time. The y-axis of these diagrams is the chemical potential energy of all of the species in the reaction at each step of the mechanism. In the first step of our mechanism, our alcohol combines together with a hydronium ion to become protonated. Notice that since we're forming the alkoxonium ion, it is higher in energy than the starting material, which has no positive charge on our alcohol. A transition state is required in order to produce this intermediate, which involves the formation of the new OH bond with the dissociation of the old HO bond in a transition state. The relative difference in energy between the starting materials and the intermediate is indicated here on the potential energy diagram with a hump as the transition state is higher in energy than both the starting materials and the intermediate due to the fact that this is the point in time in which bonds are actually forming and being broken. As such, it is very unstable. Step 1 in the diagram moves us forward to the formation of the carbocation. In this case, we have the dissociation of the oxonium ion to form the carbocation intermediate. Note that the carbocation intermediate is much higher in energy than the oxonium ion because this is a carbon with a formal charge of 1 that is missing a bond in its octet. To connect the two species together, we draw another hump that links together the two levels of energy. Up top here, we have a second transition state, which includes only the dissociation of the carbon-oxygen bond as the carbocation forms. The final step of the reaction involves the collision of the chloride anion together with the carbocation to make the alkyl chloride final product. In this case, the alkyl chloride final product is much lower in energy than the intermediate carbocation due to the fact that we've eliminated the carbocation and we have filled octets around all of our atoms in our final product. Of course, a transition state is necessary to link these two together, which is the point in time during which the sigma bond is forming between the chloride anion and the carbocation. We draw another hump indicating that the transition state is higher in energy than the carbocation by itself is, and the resultant products are lower in energy given the fact that, once again, all atoms have filled octets. If we put all three steps of the reaction together, we get the overall potential energy diagram, which you can see it's just a collection of each individual step from the previous slides. We see them together as a three-step mechanism that shows us the relative energy, chemical potential energy specifically, of all species involved in the mechanism of the substitution of an alcohol by an halo acid. So, put them all together. The step 0 is proton transfer from the alcohol to become an alkoxonium ion. Step 1 is the formation of the carbocation, in which the alkoxonium ion dissociates to form the carbocation. And step 2, the final step in the mechanism, is the capture of the carbocation by the halide anion to form our final product, which in this case was an alkyl chloride. Remember, the more stable the carbocation is, the faster it can form. This is why tertiary carbocations react much faster, is because they're more stable, right? In a sense, the relative chemical potential energy of a tertiary carbocation is much lower than the relative chemical potential energy of less highly substituted carbocations, which means it's easier to get over the energetic humps, and therefore you can get to the products faster. Early in this semester, we pointed out that primary carbocations will not form because they have no alkyl substituents to stabilize them through induction or through hyperconjugation. However, we know from empirical studies that primary alcohols can be converted to alkyl halides through substitution reactions. It turns out that this substitution reaction involves a different mechanism called the SN2 mechanism, which stands for substitution nucleophilic bimolecular. As you can see here on this slide, the last reaction from the beginning of the pre-lecture involved the formation of a primary alkyl bromide from a primary alcohol. We'll take a look at this mechanism to understand how it's possible to complete this substitution if you can't form a primary carbocation, which would be indicated by an SN1 mechanism. The SN2 mechanism is a two-step mechanism that involves the conversion of alcohols to alkyl halides without the formation of a carbocation intermediate. Step 0 of the mechanism is the same step 0 from the SN1 mechanism we just talked about. This includes the transfer of a proton from an hydronium anion to the alcohol to form the alkoxonium ion. Step 1, however, involves the bimolecular displacement of the water molecule formed in step 0 to be replaced by the halide anion without the formation of the carbocation intermediate. Let's take a look at how this works. We'll use the example from the previous slides that involves the formation of the primary alkyl bromide from a primary alcohol.
Step 0 in the mechanism should look very familiar to you by now. It involves the proton transfer from hydrogen bromide to 1-heptanol to create our oxonium ion. The oxygen atom attacks our hydrogen, cleaving the sigma bond between the hydrogen atom and the bromide to form our oxonium ion intermediate. Step 1 involves what we call the backside attack of the bromide anion with the alkoxonium ion to produce our alkyl bromide. This reaction is stereospecific in the sense that the bromine anion must come in to react with the alpha carbon from the opposite side of the molecule that the leaving group leaves from. We draw our arrows to indicate attack of the bromine lone pair on the alpha carbon and cleavage of the sigma bond between the carbon and the oxygen in the oxonium ion to produce our products, which are 1-bromoheptane and water. Be careful with considering the backside attack of your nucleophiles on your alpha carbons, because in any case in which you have a chiral alpha carbon, you will produce a specific stereoisomer in your product. Here on this slide I've included both steps of the mechanism together to show the reaction coordinate diagram. Notice the relative energy of the intermediates, reactants, and products. We start with our alcohol, go over our activation energy hump to produce our oxonium and cation in step 0. Step 1, indicated in red here, is the formation of the alkyl halide with simultaneous cleavage of the OH2 group to produce our product. This step is higher in energy because it involves the formation of the carbon-bromine sigma bond as well as the cleavage of the carbon-oxygen bond to produce our final product. There are two reactions that you should know that involve non-acidic reagents for converting ROH to RX. These are thionyl chloride and phosphorus tribromide. Although the mechanisms are included in your textbook, you are not responsible for knowing the mechanisms in this course. What you do need to know is that the combination of thionyl chloride together with an alcohol, best for primary and secondary alcohols, will produce an alkyl chloride as its product. Phosphorus tribromide is useful for primary, secondary, and tertiary alcohols to produce a alkyl bromide. You'll want to use these two reagents if you want to avoid the use of any acids that may react with other functional groups in a molecule as you're considering different synthesis. On this slide are two examples of the use of thionyl chloride and phosphorus tribromide. Note that the products are exactly what we would anticipate from the previous slide. An alcohol plus thionyl chloride replaces the OH group with the chlorine. An alcohol plus phosphorus tribromide replaces the alcohol group with a bromide. Again, you don't need to know the mechanism for these two reactions, but you do need to know the reagents necessary to complete these conversions. The last reaction and mechanism we'll look at in this pre-lecture is the halogenation of alkanes. The halogenation of alkanes occurs by a free radical mechanism in which we replace a hydrogen in an alkane with either a bromine or a chlorine from molecular bromine or molecular chlorine upon photoactivation with light. You've seen free radical mechanisms before with regard to the anti-Markovnikov addition of hydrogen bromide across an alkene in the presence of peroxide. This mechanism should look very similar to you as the mechanism that we covered last week. So remember, all free radical mechanisms are chain mechanisms that involve three types of steps: initiation steps, propagation steps, and termination steps. The first step of all free radical chain mechanisms is the initiation step, in which we form our first radical that propagates new radicals throughout the reaction. In this case, when molecular chlorine is exposed to light, a homolytic cleavage occurs in which one electron goes to each chloride from the sigma bond that the two share to form free radicals of chlorine atoms. These chlorine atoms then go forward in propagation steps by colliding with other substances in solution in order to create new radicals. Again, there are many possible types of propagation steps in any free radical chain mechanism, but we're just going to focus on those free radical propagations that get us towards the products we want. So, in this case, we can take methane and collide it with our free radical chlorine atom. Note the direction of the arrows as we talked about in lecture before. These arrows are single-headed and indicate that one electron from the sigma bond goes together with the electron from the chlorine radical to form a new sigma bond between the hydrogen atom and the chlorine. This leaves behind the other electron in the original sigma bond on the carbon atom to produce these products. Okay. In another propagation step, the methyl radical that we form can collide together with another molecule of molecular chlorine in a free radical mechanism to form a new bond between the alkyl radical and a chlorine atom, leaving behind another chlorine radical. So we get methyl chloride and a chlorine radical. Note both of these are propagation steps because in each case we start with a radical and produce a new radical. The third step that can occur in any free radical chain mechanism is a termination step. We didn't focus on termination steps last week because we were more concerned with the propagation steps that would lead us to the desired products when we were doing things like anti-Markovnikov additions. Here on this slide I've just illustrated one possible termination step. Any step that gets rid of the radicals in solution is considered a termination step. So if I were to take a chlorine radical and combine it together with a methyl radical using single-headed arrows, I would produce methyl chloride with no new radicals. This, therefore, is a termination step because no free radicals have been produced in our products. Note, chlorination and bromination can both be accomplished through free radical mechanisms. The only difference between the two is that you use molecular chlorine to chlorinate a molecule, you use molecular bromine to brominate a molecule. It is important to distinguish between the selectivity of free radical halogenation between molecular chlorine and molecular bromine. Molecular chlorine is promiscuous. It will react with hydrogens at tertiary positions, secondary positions, and primary positions with relatively equivalent rates. Notice the difference in bromination, however. Bromination occurs much more rapidly at tertiary carbons than it does at secondary carbons, than it does at primary carbons. Meaning if you want to put a halogen on a tertiary position selectively, you should choose bromination over chlorination. In fact, chlorination is only synthetically useful in cases where all of the hydrogen atoms in a molecule are equivalent to one another. Here it doesn't matter which of the hydrogens we replace around this ring because all of them are identical. No matter where you put it, you would get out the same product. Remember, use chlorination if you don't care where you want to put your chlorine halogen. Use bromination if you want to selectively place the halogen at a tertiary position. For example, here notice there are several hydrogen candidates here that could react with bromine in a free radical mechanism to be replaced with a bromine sigma bond to carbon. Only one of the hydrogens, however, is at a tertiary position, and indeed the major product we get out is bromination at that tertiary position. If you were to use chlorine instead, you could have replaced any of the hydrogens because chlorine is not selective for the tertiary position in the same way that bromine is. With that in hand, we conclude the substitution reactions that we'll be covering this week. Notice that there were two concerning alcohols that involved the replacement or substitution of the OH group with an X. That X can be chlorine, bromine, or iodine to produce the alkyl halide and water. This is our substitution of alcohols by halogen. We also introduced the substitution of alcohols with halogens with two new reagents, thionyl chloride and phosphorus tribromide. You don't need to know the mechanisms for these two, but do be able to predict the resultant products from the combination of an alcohol with either one of them. The last reaction that we learned about is the halogenation of an alkane through a free radical mechanism involving only chlorine or bromine in the presence of light to produce an alkyl halide and the resultant halo acid. That is it for the pre-lecture this week. Our pre-lecture is quite short this time around, and we'll spend the bulk of our time together in class drawing mechanisms. As always, be sure to check the relevant reading and carry and come to class prepared to apply what you've learned.